Hello. Good morning to everyone present here.
Good morning, sir.
Good morning. Okay. So just start up from just brush up the topic which I covered in the last class. Okay. So that it is visible for you people. So the PDF is visible. Okay. I'll just start up with today's class. So in the
Yes,
last
yes.
okay, so I'll just brush up the topic so that because since it is an extension of this previous day's section, so I'll just tell what and all the important things you should note down and what you are going to see the changes in the next circuit, that is a common source amplifier without source resistance we have seen. So we have analyzed the parameters as well as the characteristics parameters of the amplifier like input resistance, output resistance, so open circuit voltage gain, so normal gain as well as the overall voltage gain, everything. So what is the current, everything we have find out, expression, output voltage, input voltage, everything we have found out. And we'll see what is the changes which you will be seeing when you incorporate one resistance RS series into to the source segment. So for the existing circuit, if you are going to add one source resistance in series, so the complete characteristics, so whatever the characteristics which you have seen, so you are going to see a different characteristics, and we will see for what reason it has been changed. So that we will be analyzing the circuits side by side. Okay, so in the last class we have seen the common source amplifier. So this is a common source amplifier circuit. So you can see this is a common source amplifier circuit. So common source will be common, and gate input we are going to apply the voltage signal source voltage across the gate, and across the drain resistance you are going to get the output voltage, right? So in that case we are going to have, okay. Uh, So this is a circuit diagram of a common source amplifier. So when you are going to analyze this common source amplifier, so all the DC voltage must be connected to AC, must be connected to ground, since it is the AC signal. So DC is since it is an AC signal voltage. So when you are going to apply, so we have to connect all the DC voltage to ground, so that the drain voltage which is connected to power supply voltage is also be connected to ground, and hence the drain resistance will be connected to ground, and we are going to see the output voltage across the drain terminal. So this is a circuit diagram. So in corresponding hybrid pi model, so that is a model, that is a small signal equivalent circuit model. For this we are going to write. So this is nothing but a hybrid pi model for the corresponding MOSFET. MOSFET has been replaced with this one. And in this circuit, so we can see, so the important things, what is the input voltage? Input voltage will be appearing between what gate and source. So that is the VI. So VI will be effectively applied between the gate and ground. Hence, entire VI will be same as that of VGS. So whatever the gate to source voltage is there, so gate and source voltage, the same thing, VI will be applicable for the same. And since the gate current is not there, so the gate current flow is equal to 0. So we can say that the input resistance of this common source amplifier is infinite. And since the input amplifier input resistance is infinite, that is Rin is equal to infinite. So whatever the signal source voltage which you are going to apply to the gate terminal, so effectively all the signal will be appearing over here without any signal division loss. So voltage loss will not be there. So even though R signal as well as Rin is there, so since the Rin is equal to infinity, so effectively all the signal voltage will be appearing across the input side. So that will be applied across the VI without any loss, because Rin is having a very high value compared to that of R signal. So there will be no signal division or voltage division does not take place, or completely all the signal voltage will be coupled to the input side of the common source amplifier. So these things you should remember. So Rin is infinity, and V signal will be equal to Vi, and Vi will be equal to Vgs. So these three things you should remember in this common source amplifier. And then what is Vout? So Vout is Vout is the input output voltage which is going to appear between the drain and source terminal. So between the drain and source, the voltage, the resistance RD is connected. So across the drain resistance RD, so you can expect the output voltage. So output voltage, and if you look from the output terminal, so output terminal is between the drain. So drain terminal, if you look, so whatever the resistance which you can see, so that is nothing but the output resistance of the amplifier, that is given as R0. So this R0 is nothing but the drain resistance RD. And the same thing, MOSFET has been replaced with its corresponding equivalent circuit model. So VGS will be equal to Vi, Vi will be equal to V signal, and hence R signal will be very less. And this is a controlled current source. So voltage controlled current source it is. So it is for a given input gate to source voltage, you are going to get a control current. So that is equal to Gm times of VGS. And finally, that is a current flowing, and this is the voltage across resistance RD, and this is the output resistance R0 will be equal to RD. So in this case we have not considered the finite amount of resistance, that is neglecting the channel length modulation. So if channel length modulation is present, means we are going to model with the small R0 which is going to connect between the drain and source. So between the drain and source we are going to connect to one R0 over here. So if R0 was present, then that resistance R0, this output resistance of the amplifier will not be just equal to RD, it will be parallel combination of small R0 parallel RD. But since small R0 is nothing but it is going to have a very larger value when compared to RD. So finally, if you consider the finite amount of the output resistance of the amplifier will be yielding to, whenever there is a higher resistance value which is connected to a parallel which is of a very small value resistance, then obviously parallel combination of higher and smaller will yield to the smaller resistance. So it will be nearly equal to the lower value resistance. So obviously the output resistance will be equal to RD. So in that case you are going to consider R0 equal to RD. And open circuit voltage gain. So open circuit voltage gain means we are not connected any load resistance over here. So whatever the output voltage to input voltage, if you are going to find the gain, then that gain is called as a open circuit voltage gain. So AV0 is equal to V0 by Vi. So what is V0? So V0 is we have obtained over here. So since you can see all the analysis, Rin is equal to infinity. So Vi is equal to V signal, Vgs is equal to Vi. So output is nothing but what? So current multiply with the drain resistance. So you can see this is a current that is flowing. So Gm into Vgs is the current that is flowing, and this is the output resistance RD. So Gm into Vgs into RD. So minus symbol because it is a output voltage will be 180 degree out of phase. So minus Gm into Vgs into RD, that is the output voltage expression. So I can write V0 is equal to what? So minus Gm into Vgs is current into resistance. So minus Gm into Vgs into RD. And finally output resistance, so we can, how we are going to find out output resistance? So output resistance ಕಂಡುಹಿಡಿಯಬೇಕು ಅಂದ್ರೆ ಯಾವುದೇ any amplifier, we have to set the signal voltage to 0. V signal is equal to 0. So Vi will be equal to 0. So Vgs is equal to 0. So now input side there is no contribution of the resistance, which is going to have effect on the output resistance calculation. So since it is a unilateral, so unilateral means there is no loading effect from the input side to output side or output side to input side when you are going to calculate the resistance. Okay, so ಇವಾಗ resistance calculate ಮಾಡಬೇಕಂದ್ರೆ, so input resistance calculate ಮಾಡಬೇಕು ಅಂದ್ರೆ what is the, how we are going to find the input resistance calculate ಮಾಡಬೇಕು ಅಂದ್ರೆ it is a combination of R signal and Rin. So Rin is nothing but infinity, so this is going to have a high input resistance. Whereas when we are going to calculate this, so this RD, that is the resistance output resistance RD, is not going to have any impact on the input resistance calculation. Whereas when we are going to find out the output resistance, so this input resistance is not going to have any impact because it is not connected. So nowhere the input from the gate and drain is connected. Hence, so there is no what we call, so in control systems and all network analysis, and you might have seen the Miller effect, Miller capacitance, Miller resistance ಅಂತ ಹೇಳ್ತಾರೆ. So that is a Miller effect ಅಂದ್ರೆ, so whenever you are going to have a feedback path ಅಲ್ಲಿ, so when you are going to have a connection between the output to input, so through any passive components like capacitors or resistance, so those resistance and capacitance will have impact on both input side as well as the output side. In that case we are going to see the Miller effect. Okay, in the next chapters and all we are going to see in that case when we are going to talk about the feedback or negative feedback chapter, when we are going to discuss. So in that case we are going to have some resistance which is going to connect this one. But here in this case, this discrete circuit common source amplifier only, output and input there is no effect. So there is no loading effect which can be seen from input to output or output to input. Hence, this type of amplifiers is called as unilateral amplifiers. Okay, unilateral amplifiers. And here you can see the output resistance is just equal to RD, and the way you are going to calculate is by connecting test voltage source across the output and test current source, and we are going to find out what is the voltage drop over there, so that you are going to find out the output resistance. And then what is the output voltage? So if you are going to have a load resistance has been connected across the output means, so finally the output voltage will be appearing across the load resistance means, the open circuit voltage, whatever the output voltage you are going to get without connecting the load, that is the unloaded amplifier, that output will get divided across the load resistance as well as the output resistance of the amplifier proper. So in that case the output voltage will get divided. So this is the expression. So AV naught into Vi is the output voltage of a amplifier, wherein which we are not considered any the load resistance. So that output voltage multiply with, that is this output voltage will get divided across the RL, and total resistance will be RL plus R0. So that gives the final output voltage across the load resistance RL. So this is how the output voltage when you are going to have a load resistance connected. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? So whether you are following or what? Hello? Anybody reply me whether you are understanding or what?
ಸರ್ ಕೇಳಿಸ್ತದೆ.
ಕೇಳಿಸ್ತಾ ಇದೆ, ಗೊತ್ತಾಯ್ತು. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? ಎಸ್ಟರ್ಡೇ ಮಾಡಿರೋದೇನೋ yesterday class. Okay, so I'm not teaching any different, so yesterday class only. So this is how the output voltage will be getting when we are going to have a load resistance. So illi load resistance connect madilla, so we have not shown, but if you are going to connect on load resistance means this output voltage is nothing but what? So that is the open circuit output voltage. So this is nothing but open circuit voltage. So output voltage, this output voltage will get divided. So if it is the output voltage ittu andre illi, so here also one resistance, output resistance is there, and another load resistance ittu andre, so this output voltage will be gets divided across these two resistance, so that you will get some drop over here. So that will be the final output. So our final output voltage across load resistance barbeku andre, this output voltage is nothing but open circuit output voltage. So open circuit output voltage gets divided across here. So we are going to have this expression AV naught times of Vi is nothing but output voltage without load resistance. That output voltage multiply with RL divided by total RL plus R0. That gives the final output voltage across the load resistance RL. Okay. So next, so we need to find out what is the voltage gain of the amplifier. So voltage gain of the amplifier andre we are going to consider the load resistance. Okay. So load resistance consider ಮಾಡ್ಕೊಂತೀವಿ. And if we consider Vi, so AV naught times of Vi, so this is nothing but this is the output voltage. So output voltage divided by input voltage, that gives the voltage gain of the amplifier. So this output voltage divided by Vi anta madidre, so this Vi will get cancelled. Finally the output voltage of the amplifier will be getting as this expression. So output voltage ಕಂಡುಹಿಡಿದ್ವಿ for a loaded amplifier. So next is we need to find out this one, no? So we have already found out output voltage, so divide by Vi, so that gives this amplifier gain, so voltage gain. So V naught ಕಂಡುಹಿಡಿದಿವಿ, divide by Vi ಮಾಡಿದ್ರೆ, so Vi will get cancelled and left out with this parameter. This is nothing but voltage gain of the amplifier proper AV. Okay. Now GV, so overall voltage gain ಕಂಡುಹಿಡಿಬೇಕು ಅಂದ್ರೆ ಏನು ಮಾಡಬೇಕು? So overall voltage gain ಕಂಡುಹಿಡಿಬೇಕು ಅಂದ್ರೆ across the load resistance whatever the output voltage is there towards the V signal we have to find out. But output voltage across the load resistance towards here will be same as that of here because of high input resistance, because of the input resistance is infinite value. So signal voltage as well as the input voltage there is no difference. So Vi will be equal to V signal will be equal to Vgs, and hence whatever the voltage gain you are going to get for the voltage gain of the amplifier proper, the same voltage gain you are going to get. So V naught by V signal. So V naught anytime, so this is the output voltage across the load, so you write as it is and divide by V signal. V signal will be same as that of Vi, so Vi will get cancelled, and again the expression for the overall voltage gain will be getting as same. So instead of this, you can also write. So Vi can be expressed as what? So Vi will be can be expressed as what? So Vi can be expressed as a V signal into Rn divided by R signal plus Rn anta ಮಾಡ್ಕೊಬಹುದು. Since Rn is infinity, so this will not have impact. So V signal can be approximated to Vi. So the same thing he has written over here. So GV is V naught by V signal. No? So we are going to write as it is the output voltage or whatever you are going to get this one. No, so this expression as it is we are going to kept as it is. Okay, these things we have kept. So but in place of Vi, so we are going to write it as what? V signal into Rn divided by Rn plus R signal ಮಾಡಿದಾಗ so Vi will be expressed as V signal ಅಂತ ಬಂತು. So this V naught by V signal, if you take the ratio, so this will be the gain, overall voltage gain. But Rin is infinity ಇರೋದ್ರಿಂದ, so entire thing, so it will be gets cancelled and it will be left out with this voltage gain expression. Okay, so the gain expression for the overall voltage gain also it will be remain same as this, since because Rin is infinity, so whatever the maximum and infinity by infinity, so that means this maximum resistance is there and this is not going to have any contribution, so it is going to have a factor of 1. Okay, so numerator also same, denominator also same, so it will get cancelled and left out with this expression. So this is nothing but the overall voltage gain. This overall voltage gain as well as the voltage gain of the amplifier proper, both are same. Okay, so that is the thing which you are going to get. So in terms of gain expression, if we write, so AV naught is nothing but voltage gain, so that will be equal to minus GM times of RD. So that is the voltage gain of overall circuit voltage gain. So AV naught ಇಲ್ಲಿ ಎಷ್ಟು ಬಂದಿತ್ತು, so AV naught ಹೆಂಗೆ ಕಂಡುಹಿಡಿದಿದೆ ಅಂದರೆ, so in terms of output voltage, overall voltage gain we have found out. So AV naught times of Vi. So here if you are going to find out the overall voltage gain, so V naught by Vi, so that will be gain expression, so it will be equal to minus Gm times of Rd, so which we have already found out in the small signal operation of a model of a MOSFET. So first module alli small signal operation model ಮಾಡಬೇಕಾದ್ರೆ what is the voltage gain ಕಂಡುಹಿಡಿದ್ವಿ, so that same thing we are going to find out here. So minus Gm into Rd is the voltage gain. So now for this voltage gain ಕಂಡುಹಿಡಿದ್ವಿ, so if it is RL is connected parallel means Rd parallel RL ಆಗುತ್ತೆ, so that is the gain. So AV naught is nothing but minus Gm into Rd, so minus Gm into Rd into RL. So RD RL parallel ಇರುತ್ತೆ, so AV naught is minus GM into RD parallel RL, so that is the gain expression you will be getting. The same thing you will be getting for the overall voltage gain as this expression, minus GM into RD parallel RL. So this is about the common source. So with this recap of this common source, so I will be just starting with the common source amplifier with a source resistance. Okay, so common source amplifier with the source resistance. So for the previous circuit, whatever you have done, so the same thing you are going to write the circuit diagram for this one common source, but only thing you are going to have change is nothing but the source resistance Rs. So by connecting Rs to the source terminal, Rs has been connected across the source terminal. Now the modification so is only this resistance. By adding this resistance, rest of that all remains same. So what is the now with this incorporation or with this inclusion of this resistance Rs? So what and all it is going to change, we have to observe. So now if we carefully look at this expression, so for a time being you just forget about this small signal operation model, only you just concentrate on this circuit diagram, common source with source resistance added, and gate input we are going to give a signal source along with a signal source resistance, and across the output you are going to have a drain resistance Rd, and across the output you are going to have a final output voltage. So from the drain terminal, if you look at the resistance, so we will be having what, so we can see the output drain terminal alli yav resistance ide, so that is the drain resistance, so we can call R naught as a equivalent to Rd. But now what is the input voltage now? So if you come to the input side, so what is input voltage? This is nothing but the input voltage between what, gate terminal and ground. So input voltage is Vi. So now whether the same input voltage is same as that of VGS? No. So here it is gate voltage is there, here source voltage is there, so Vi will be equal to VGS plus Vs. Okay, so Vi, effective input voltage Vi will be equal to VGS gate to source voltage VGS plus Vs. Okay, so that together it will be equal to Vi. So that means the effective input voltage will be equal to the sum of the gate to source voltage plus source voltage across the source resistance. Whatever the voltage drop across RS is there, that is Vs, and between gate and source some voltage drop will be there, that is given as what? That is VGS. Okay, now what is the input resistance now? So input resistance, whether any current is flowing across the gate to drain or gate to source, no current is flowing. Hence again the Rin is equal to infinity only, because the gate current, whenever you are applying any input voltage to the gate terminal, there will be no current flowing. Hence the gate input side will be having a infinite resistance. That means the current flowing is zero. So input resistance of this amplifier will be equal to infinite. So these things should be common. Okay. So now for this circuit to write its corresponding small signal equivalent circuit, so they have modified the small signal equivalent circuit model over here. So this small signal modification is being obtained because of the some alternative. So some what do we say? So some modification in the small signal model has led to this equivalent circuit model. Okay, so we will see, this is not there in your syllabus, but I will just show that PDF, and I will tell how this model has been obtained from the small signal equivalent circuit model. Okay, so up to here it is okay, right? So small signal common source with the source resistance in series, this is a circuit model. So corresponding small signal equivalent circuit model, so we are going to modify the small signal for the analysis purpose. To make the analysis purpose easier, so we are going to modify the small signal operation model to make it simple. So to make it the simpler analysis, so we are going to modify that one. So I'll just show the corresponding small signal equivalent circuit model. So in this circuit, you can see this is the small signal operation of the model, right? So this is a small signal operation of the model. So wherein which you can see the gate is there. So source is common. So gate is the input and drain is the output. And between the drain and source, you are going to have a constant current that is flowing. So which is the current that will be controlled from the gate to source, that is voltage control current source. So that is the current that is flowing. So Gm times of Vgs. So this is the controlled current source. Okay, so voltage controlled current source, and between the gate and source, so there is no resistance or anything. So because the current is not flowing between gate and source, so the input gate to source voltage is directly applicable. So and there will be input resistance will be infinite only. So that is the small signal operation of the model. So drain current here flowing, so Ig is equal to 0. So only the voltage Vgs is going to apply between the gate and source, and here the source current is flowing. So whatever the drain is current is there, the source it is going to have the same, so source current. So this is the small signal model. So now this small signal model, so some of the analysis it will be difficult. So in order to make it simpler, so we are going to write the same modification, some little alternative of this arrangement. A small signal model will lead to an new model which is going to be have a easier to analysis. So easier for easy understanding, as well as easier to calculate and calculate the terminal currents as well as terminal voltages. So we are going to alternate this small signal model to corresponding equivalent circuit. So what we are going to add is the, so from this small signal model, so we are going to add another constant current source. So what is this Gm into Vgs? This is the current that is flowing between drain to source. So if I am going to have another Gm into Vgs, that is another current if I am going to connect. So whether there is any changes in the terminal current? Hello, students.
Yes, sir.
If I am going to add another current source, okay, so current which is of same value, so Gm into Vgs, here also Gm into Vgs is there. So if I am going to add another current source in series, whether there is going to change any terminal currents is going to change. between the two terminal drain and source, I am going to add another controlled current source in series to the original control current source. So this is the original. For this I am going to add another current source in series. So whether the terminal currents is going to change now?
No, sir.
It is not going to change any current, because the same current source, if I am going to have the same value of the current, means Gm into Vgs, and here is also Gm into Vgs, that is the current terminal between the drain terminal and the source terminal. If I am adding another current source also, it is not going to vary any terminal current characteristics. So ID will remain same as that of Gm into Vgs, and here also Gm into Vgs between the drain and source. And by adding another current source, we are going to add one node point X. Okay, so this is the modification. So here, since the drain to source, one current source was there, so now I am going to add another current source in series, and we are going to insert one node X. Okay, so indicating this is the slight modification to this one. So whether the this model and this model is same? Yes. So this is also same, and this is also same only. So because the current terminal current characteristics, voltage and all, it is not going to change anything. So this model is also same, and this model is also same. Okay. So from this I am just making connection of this node X point to this one, and making sure that there is no gate current. So there is no gate current, and the gate current is not going to be changed. So I am going to modify from this model to the next model. So as this, by connecting that node X point to the gate terminal, such a way that I am not going to vary any terminal current characteristics. There is no change in the terminal characteristics. So Ig is again, it is same as that of previous value. So Ig is equal to 0. Here also it is going to have the same, even though if it is connected, the current is not flowing over here, and the current is going to flow over from this point to this point itself. So Gm into Vgs, and X node is connected to now the gate terminal, and resulting circuit is remain same as that of previous. Okay, so now this X point, so I am going to make such a way that so I am going to say this gate current is connected in a T form. Okay, this is a gate, and this is a drain, and this is source. So this is gate which has been connected over here, so Ig is equal to 0, and this is the drain, so this is drain terminal is remains same as that of point. So this is X point, so I have not labeled X point over here, but this point is nothing but X point only. Okay, so this point is a drain terminal. So here you can see the drain current is flowing from the drain point terminal to this node. So from this drain terminal to this node, the current is flowing Gm into Vgs. It is going to remain same, and between the gate and source. So between the gate and source, so you are going to have a model. So we are going to change such a way that the current flowing is not varied. So you are going to have, because gate to source voltage is there, and if I am going to have one resistance which is going to have between the gate and source, such a way that it is not going to vary the terminal current characteristics. So ID value is not going to, should not change, such a way that you are going to add one resistance in series. So between the gate and source, we are going to have, so this is a gate and gate in the source. So within the gate node point this, and this source, not this from here, from that node point to the source node. So we are going to incorporate one resistance, so that resistance, so by incorporating, it should not vary the current Gm into Vgs. The current should not vary, they should be equal to Gm into Vgs. So how you are going to do? So R is equal to, so you are going to have this resistance, right? So this resistance value, how much it should be? So resistance value should be equal to, R is equal to V by I, right? So what is R? So R is equal to V. V is what? So Vgs. So Vgs divided by I is what? Gm divided by Vgs, right? So ID is nothing but a Gm into Vgs. So you are going to have this is the gate to source voltage, and this is nothing but the a current that is flowing. So R is equal to V by I. So Vgs will get cancelled, and this is going to equivalent to that of the 1 over transconductance parameter Gm, 1 over Gm. So this will be the value of the resistance which you are going to add over here. So by adding this, so the resistance value is going to have equal to 1 over Gm. So now we can see, so what is the current which will be flowing? V is equal, I is equal to what? V is equal to IR, I is equal to V is equal to IR, right? So current Beko. So now I need to see what is the current that is flowing. I is equal to what? V is equal to IR. I is equal to V by R. So V divided by R. So VGS divided by 1 over GM. So again the current will be remain same as that of GM times of VGS. Correct? So any changes it is going to happen now. So IS is equal to what? So I is equal to V by R. So V is what? So gate to source voltage, and R is what? 1 over GM. So it is again the source current will be again remain same as that of GM times of VGS as that of original model. So whatever the source current it should be have, so it should have some same GM into VGS. So now the small signal equivalent circuit can be represented like this, right? So any changes we are going to see like this from this model to this model. If we look at the if we look at the expression, so the T equivalent model, there is no change in the terminal characteristics. So we can adopt this model as a small signal operation model, as the current, terminal current as well as the terminal voltages are not going to vary. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? So I can write this as a T equivalent model. Why it is T equivalent? So you can see this is like a T model. So this is used for MOSFET analysis. So ಯಾಕೆ ಈ ತರ ಮಾಡೆಲ್ ಅನ್ನು ಮಾಡಿಫೈ ಮಾಡಿದ್ದಾರೆ? So that is not modified, it is just an alternative representation of the small signal model. So this is the small signal model and corresponding alternative representation by using the T equivalent model. So T equivalent model ಮತ್ತೆ small signal model ಏನು ವ್ಯತ್ಯಾಸ ಇಲ್ಲ. So current ID, what was the current which is flowing, that is remaining same across the ES also. So whatever the gate current is flowing, that is 0. The same thing here also it is flowing 0. So what is the current ID is there, so that is GM into VGS, that is same thing is there. And we have not interrupted or we have not added anything. So just modification of this small signal has been obtained as a new model, and it is nothing but a T equivalent circuit model. Okay, so this T equivalent circuit model ಯಾಕೆ ಹೇಳ್ತಾ ಇದ್ದೀನಿ ಅಂದ್ರೆ, so this will be seen in the analysis of the coming common source with source resistance. So whenever the source resistance has been added in series, so instead if we are going for a normal representation, so this source if you go for the normal representation ಮಾಡಿದಾಗ ಏನಾಗುತ್ತೆ, ಸೊ ಇಲ್ಲಿ ಸೋರ್ಸ್ ಹತ್ರ ಇನ್ನೊಂದು ರೆಸಿಸ್ಟೆನ್ಸ್ ಒಂದು ಆಡೆಡ್ ಆಗಿದೆ ಅಲ್ವಾ, ಸೊ ಸೋರ್ಸ್ ಹತ್ರ ಇನ್ನೊಂದು ಸೋರ್ಸ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಆಡೆಡ್ ಆಗಿದೆ. So when we are going to do, so this will become complicate the analysis. If you are going with this model, complicate ಆಗುತ್ತೆ. So for that the complication, in order to avoid the complication, so what we are going to do, so we are going to do with this T equivalent circuit. So ಯಾಕಂದ್ರೆ ಸೋರ್ಸ್ ಟರ್ಮಿನಲ್ ಹತ್ರ ಗ್ರೌಂಡ್ ಆಗಿಲ್ಲ, ಸೊ ಇನ್ಸ್ಟೆಡ್ ಸೋರ್ಸ್ ಟರ್ಮಿನಲ್ ಹತ್ರ ಒಂದು ರೆಸಿಸ್ಟೆನ್ಸ್ ಆಗ್ಬಿಟ್ಟು ಒಂದು ರೆಸಿಸ್ಟೆನ್ಸ್ ಆಡೆಡ್ ಆಗ್ಬಿಟ್ಟು ಆಮೇಲೆ ಕನೆಕ್ಟೆಡ್ ಟು ಗ್ರೌಂಡ್. ಸೊ with this ಮಾಡಿದಾಗ, so there will be little confusion or little difficulty in analyzing the configuration and all. So for that reason, so we have just a model and we are going for T equivalent circuit model. So that T equivalent circuit model you can observe in this figure. Okay, so in place of MOSFET, so this common source MOSFET, so this MOSFET has been replaced with its small signal equivalent model, which is called as a T equivalent circuit model. So T equivalent circuit model I have just incorporated over here. Only thing is that analysis will become simpler. Adu ondakoskara we have just implemented a T equivalent circuit model. So now T equivalent circuit model, so you can see and we can see the analysis. R signal, V signal same, R signal, V signal is same. So gate current as gate current is 0, so the same thing. And what is the I? I is nothing but the drain current, so which will be equal to what? GM into VGS, the same thing. And what is the resistance over here? So that is 1 over GM. So that is a T equivalent circuit model. The same thing here, we are going to have the same resistance, which is going to have 1 over GM as a resistance, and the current which is flowing over here, the current which is flowing over here will be remain same. Okay, and the gate current is 0. And now between the gate and source terminal, so this is the source terminal, right? So source terminal we are going to add one resistance. So from the source is not directly connected to ground, instead it has been connected to one resistance and then it is being connected to ground. So source terminal will be connected with the source resistance. So the source resistance has been added and then it has been connected to ground. And now what is the input voltage? So this is the input voltage. So input voltage ಎಲ್ಲಾಗ್ತಿದೆ, ಗೇಟು ಮತ್ತೆ ಗ್ರೌಂಡ್ ಮಧ್ಯದಲ್ಲಿ input voltage we are going to see. The same thing here also. Vi is going to apply between gate and ground. Okay, so between gate and ground, what is the voltage which you can see here? So gate voltage, gate terminal ಮತ್ತು source ಮಧ್ಯದಲ್ಲಿ gate to source voltage ಇದೆ. Okay, so you can see this is the gate terminal and source terminal. So between gate and source, you are going to have a across the this resistance, you are going to have what? Gate to source voltage VGS ಇದೆ. ಆಮೇಲೆ so we can see from the source we are going to have one resistance. So from across here, so it will be having what? Source voltage will be there. So source voltage ಅಂದ್ರೆ ಏನು? So the voltage across the resistance RS will be source voltage plus VGS. That together VGS plus VS, that will be equal to the value of VI. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? So now what is the resistance which we can see from the input side? That is input side ಅಂದ್ರೆ ಯಾವುದು? Gate terminal. So if we look at from the input side, what is the resistance offered? Since the gate current itself is zero, there is no current flowing across the gate. So obviously the input resistance will be equal to infinity. Okay, so there is no change in the previous analysis and this analysis. So Rin will be equal to infinity. And then what is the resistance when you look from the output terminal drain? So drain terminal indaga nodidaga, what is the between the drain terminal and ground? So what is the output resistance? So you can see this is the resistance RD. So RD is there, so which is connected between drain terminal and ground. So this is the obviously the output resistance. So we are not going to consider the RL as of now. And now another important thing which we have to discuss here is so we are not going to consider the channel length modulation. So channel length modulation effect we are not going to have. So if we consider the channel length modulation, so it is going to become a complex. So complex it is going to have a complex in the circuit. So ಏನಾಗುತ್ತೆ between drain and source ಅಲ್ಲಿ, so we are going to have one finite amount of resistance R naught. So that R naught ಬಂತು ಅಂದ್ರೆ, so the analysis of the circuit or the analysis of the common source amplifier will become complicated. So for that reason we are not going to have the finite amount of resistance R naught. That means channel length modulation effect consider ಮಾಡ್ತಿಲ್ಲ. So lambda will be equal to 0 ಅಂತ consider ಮಾಡ್ಕೊಂಡ್ಬಿಟ್ಟು, so we are going to do the analysis for common source with source resistance with the T circuit equivalent model. So R naught will be equal to finally the output resistance RD itself. So since lambda channel length modulation effect is not there, so lambda is equal to 0. So we are going to have only from the output terminal output resistance ನೋಡಿದಾಗ, so we are going to observe only the drain resistance as the output resistance of the amplifier. So I can write R naught will be equal to RD. Okay, so without unloaded, so whatever the output voltage to input voltage, if you are going to find, that is nothing but open circuit voltage gain. So whether you are following, so now we are going to analyze the common source amplifier with source resistance. So that is the circuit without bias details. So this is the circuit diagram without bias details, and now equivalent circuit with the MOSFET represented by its equivalent T model. So this is a T model which have been obtained from the previous. So that I will share that PDF also, so that you will understand what is the change. So in the small signal MOSFET model go, T equivalent circuit model go, what is the change we can see. And this is a T equivalent circuit model we are going to have. So whenever we are going to have a resistance has been connected in the source load, so T model is usually preferred, so because it is going to make the analysis simpler. So for that analysis simpler igoskara, so whenever resistance has been added in source hatra resistance add ಮಾಡಿದಾಗ, so it is going to complicate the analysis. Hence in order to simplify, so we are going to work T model. So we see that the input resistance Rin is infinity. So we know that Rin is infinity because Ig is equal to 0. So Rin is equal to infinity ಆಗ್ತಿದ್ದಂಗೆ, what is the value of Vi? So Vi will be equal to the same as that of V signal itself. So the same thing. So Vi will be equal to V signal, but Vi is not equal to Vgs now. So in the previous case only, V signal was equal to Vi, Vi was equal to Vgs. Between the gate and source directly there was no since the source was directly shorted to ground, so Vgs was equal to Vi and Vi was equal to V signal anta madidve. But now V signal is equal to Vi. So again the input, since Rin is equal to infinity, the signal source resistance is not going to have any voltage drop, so that effectively all the signal voltage will be appearing across the Vi without any loss. So Vi will be equal to V signal source voltage. Okay, unlike the source, unlike the source amplifier, common source amplifier, and the previous case ಅಲ್ಲಿ common source amplifier ಅಲ್ಲಿ ಏನಾಗಿತ್ತು, only fraction of Vi will be appearing between the gate and source. So in the previous case ಅಲ್ಲಿ Vi was equal to Vgs, but now Vi ಅಲ್ಲಿ ಏನಿದೆ ಅದರ fraction of the in Vi will be appearing across Vgs and remaining will be appearing across the Rs. So fraction of Vi will be appearing across the gate to source and remaining fraction will be appearing across the source resistance Rs. So that is what you are going to see here. So common source amplifier Vi will be equal to Vgs, but now Vgs will be what? So fraction of the input voltage will be appearing across the Vgs. So Vgs is to, now if I want to find what is the value of Vgs, so Vgs ಕಂಡುಹಿಡಿಯಬೇಕು ಅಂದ್ರೆ ಎಷ್ಟು ಮಾಡಬೇಕು, what is the value? So Vi is the input voltage, so Vi will gets divided across Rs as well as 1 over Gm. So the Vi will gets potentially divided across 1 over Gm as well as Rs. So Vgs will be equal to Vi into 1 over Gm divided by 1 over Gm plus Rs. So that is the Vgs value. So Vgs will be equal to what? Vi multiply with 1 over Gm. So across what the voltage we are going to get. So across which resistance you are going to find. So the voltage Vi will gets divided across 1 over Gm divided by the total resistance across this one, 1 over Gm plus Ra. So what is the value of Vgs? So Vgs value will be now what? So if I simplify this equation, so 1 over Gm taken as common means 1 plus in the denominator 1 plus Gm into Rs will be there, and Gm will get cancelled. So Vi divided by 1 plus Gm into Rs you will be getting. So this will be the value of the gate to source voltage Vgs. So Vgs will be equal to what? So Vgs will be equal to Vi divided by 1 plus Gm into Rs. So you can say, so the gate to source voltage will be equal to the voltage, how much it is going to reduce, divided by 1 plus Gm times of Rs value, it is going to reduce the input voltage. So this is about the gate to source voltage. So now coming to the output voltage. What is the output voltage? So output voltage will be equal to what? So the current which is going to across the flow, what is the current that is flowing across the output terminal? I multiply with Rd, that gives the value of the output resistance. Since the drain to source will be having 180-degree out of phase, so minus 1 I into Rd, that will be the output current. So output voltage will be equal to minus I times of Rd. So what is the value of I we need to find out now. So this simply they have given, we have just taken what is the output voltage. So output voltage is nothing but V is equal to IR. So what is the output current? I. And what is the output resistance? Rd. So we know that, so minus Y into Rd. So what is the value of I we need to find out. So the current I is nothing but the drain current which is flowing from the drain terminal towards the source terminal. The current is I. So we need to find out what is I. So what is I? Across the input side, if you consider what is the I, so input side alli consider madre. So this is the current that is flowing. So since the current flowing over here is 0, so from this node towards this one, the current flowing is I. So I will be equal to the current that will be equal to Vi. So that is I is equal to V by R, right? So what is Vi? So that is the input voltage. So from here to, from this node to this node, the voltage is what? So Vi. So we know that this is the current that is flowing across the I. So this is the across the 1 over Gm is also I, as well as across the source resistance is also the same current is flowing. So we know that what is the voltage drop from this node to this node, that is Vi, and what is the current we know, so that is the I current. So from that, what is the total resistance from this node to this node is what? So 1 over Gm plus Rs is there. So I can easily find out what is the value of current I. So I will be equal to Vi divided by 1 over Gm plus Rs. So that will be the value of the current. So I will be equal to the voltage Vi divided by the total resistance. So total resistance is what? 1 over Gm plus Rs. So 1 over Gm plus Rs, simplify this one. So you will be getting Gm divided by 1 plus Gm into Rs. Simplify this equation. 1 plus Gm into Rs. Gm will go to the numerator. So Gm into Gm divided by 1 plus Gm into Rs. So now if we carefully look at this expression, what is the value of the current? I is nothing but output current. And what is this value? So this is one numerical, so this is some constant is there. That is Gm divided by 1 plus Gm into Rs is a constant. Multiply with Vi. So Vi is what? So that is the input voltage. So here if we consider the relation, so output current is there, input voltage is there. So you can say that this entire parameter which is there inside the bracket is nothing but a transconductance parameter for a common source with source resistance. Is it not? So this is the output current I, and the relation between the output current and input voltage is what? So that is nothing but a transconductance parameter. So if we see the transconductance parameter, so previous ಏನಿತ್ತು transconductance ID will be equal to GM times of VGS, that is the current, right? So same thing here also, I is nothing but ID only, drain current. So VI is nothing but the input voltage. So but the transconductance is now what? GM divided by 1 plus GM into RS. That means if we look at this expression, the transconductance has been reduced by a factor of 1 plus GM into RS. So E circuit ಅಲ್ಲಿ, so by incorporating the value of the, by inclusion of resistance in the source terminal is going to reduce the overall transconductance. Overall transconductance ಎಷ್ಟಿತ್ತು? GM into VGS ಇತ್ತು. In the, when we are going to have a previous analysis ಮಾಡಿದಾಗ, so ID, that is the output voltage, output current will be equal to what? Input gate to source voltage multiply with the transconductance GM times of VGS ಇತ್ತು. But now GM into VGS ಬದಲು, so here GM into VI, GM divided by 1 plus GM into RS ಅಂತ ಇದೆ. That means the normal transconductance ಗಿಂತ it is going to be a reduced value. So common source ಅಲ್ಲಿ, without source resistance ಅಲ್ಲಿ transconductance value was very much higher, but now common source with source resistance ಅಲ್ಲಿ, so the transconductance value has been reduced by a factor of 1 plus GM into RS. ಯಾಕಂದ್ರೆ, so normal transconductance divided by 1 plus GM into RS means you forget about 1 here, GM into RS. So what is the value of resistance? Whatever it might be, multiply with this. So you will be having a denominator term will be there. So it is going to reduce the normal transconductance GM. So it will be equal to 1 by so GM divided by GM into RS ಅಂತನೇ ಮಾಡ್ಕೊಳ್ಳಿ. GM will get cancelled and it will be equal to 1 by RS. So resistance whatever it is there, so the transconductance value is going to have a inverse of 1 over RS you will be getting. So when you are going to have a resistance in series. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? Whether you are following or what? Students, I am asking you one
ಅರ್ಥ
thing.
ಆಗ್ತದೆ ಸರ್.
So what about others? So I have not just done anything.
Yes,
So
sir, ಅರ್ಥ ಆಗ್ತಿದೆ.
ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? Okay. So this is the current. So current in the, so we are going to obtain the relation between the current and the input voltage, that is the transconductance relation. So ಹೆಂಗೆ start ಮಾಡಬೇಕು? So I am going to start what is the VGS value find out ಮಾಡಬೇಕು. ಆಮೇಲೆ so VGS value ಮಾಡಿದಾಗ, so what is the current flow ಆಗೋದು between the drain and source. So we need to find out this one. So in order to find out this, so first we need to find out what is output voltage. So input voltage ಏನು ಅಂತ ಕಂಡುಹಿಡಿಯಬೇಕು. So normal thing is that input voltage, first input resistance calculate ಮಾಡಬೇಕು, ಆಮೇಲೆ input voltage calculate ಮಾಡಬೇಕು, what is output voltage calculate ಮಾಡಬೇಕು, what is current which is flowing we have to find out, and then we need to find out open circuit voltage gain, normal voltage gain, as well as the overall voltage gain. So all these 5 parameters we need to find out. So what is the input voltage? So input voltage will be reduced by a factor of this one, as well as the output voltage is this one, and what is the current expression we need to find. So current ಎಷ್ಟು ಅಂತ we have found out, and now we need to find out the open circuit voltage gain AV0. So open circuit voltage gain ಅಂತಿದಂಗೆ, so you should remember that there will be no load resistance, and the gain which you are going to find out without a load resistance is called as open circuit voltage gain. So AV0 is equal to what? So ಈ AV0 ಕಂಡುಹಿಡಿಯೋಕೆ, so we should know what is V0 as well as what is VI. So VI ಎಷ್ಟು ಅಂತ ಗೊತ್ತಿರಬೇಕು, as well as V0 ಗೊತ್ತಿರಬೇಕು. So V0 is going to find. So what is V0? So V0 is equal to what? Minus I into RD. So what is I? I is given as this. So this multiply with RD, that gives the value of V0. So multiply this. So the GM into RD divided by 1 plus GM into RS divided by VI is there. So VI divided ಮಾಡಿದ್ರೆ, so VI will get cancelled, and this is the expression you are going to get. So if we carefully look at this expression, open circuit voltage gain without load resistance, so without source resistance ಇದ್ದಾಗ it was just equal to minus GM into RD. So minus Gm into Rd was the open circuit voltage gain. So previous expression only. So you can see over here. So what is open circuit voltage gain? So common source without source resistance iddaga, it is just equal to minus Gm into Rd without source resistance, first topic. But now adding source resistance in series to this source terminal, now if we find out the value of the open circuit voltage gain, so you will be getting minus Gm into Rd same divided by 1 plus Gm into Rs you are going to have. So what is this meaning is, so the open circuit voltage gain is going to be reduced by a factor of 1 plus Gm into Rs. So only thing is that, so this source resistance is going to act like a negative feedback. So this negative feedback only in what are the important properties is there. So it is going to reduce the gain. So negative feedback and positive feedback only, what is the difference is, negative feedback is normally used in order to control the gain. So whenever we need to control the gain, so we are going to use for negative feedback. And by doing negative feedback, by employing negative feedback, what is the disadvantage you are going to have is the gain is going to reduce. At the same time, advantage which you are going to have in negative feedback is the bandwidth is going to increase. The extension of bandwidth you are going to get when you employ a negative feedback. So there are some important properties. So here you can see the voltage gain has been reduced. So what is the previous, without source resistance it was equal to minus Gm into Rd, but now on adding source resistance the gain has been reduced by a factor of 1 plus Gm into Rs. So open circuit voltage gain is minus Gm into Rd divided by 1 plus Gm into Rs. So this expression indicates what? The gain has been reduced. So now I can just represent in terms of another way, so which can also be expressed. So Gm common takonಡ್ರೆ, so Rd divided by minus 1 over Gm plus Rs. So the same thing in the numerator or denominator change ಮಾಡ್ಕೊಂಡ್ರೆ, so this expression can be written as this. Okay, so there is nothing to do with this one. Okay, so what is the final output resistance if you consider a load resistance has been connected? So load resistance RL connect ಆಗಿದೆ ಅಂದಾಗ at the output side. So what is the gain? So this is the gain, right? So open circuit voltage gain is nothing but voltage gain. So AV0 into VI. So AV0 into VI is the output voltage without load. So if you are going to have a load resistance itondre, so this one AV0 into VI. So this is nothing but AV0 into VI is nothing but output voltage without load resistance is there. So this output voltage will get again divided across the load resistance RL. So this output voltage is the without load resistance AV0 into VI into RL divided by RL plus R0. R0 is given as what? So R0 is given as RD. So R0 is given as RD. So AV is equal to the overall gain. So which will be having the load resistance. So you can say that the RD parallel with so here if you are going to have a load resistance connected over here. So the final output voltage will be appearing across this load resistance RL. So this V0 will be equal to this V0 AV0 open circuit voltage gain into VI into RL divided by RD plus RL. So that will be the voltage gain AV. So AV will be equal to, so the same thing, parallel combination of RD and RL will exist. So minus Gm times of RD parallel RL. So this is going to have over here. And then, so this is the expression for the overall voltage gain. So this is the open circuit voltage gain. And then if we consider alternately we can simplify the resistance RD. So RD parallel RL anta madkondo, so you will be getting this as the gain. So this is how you are going to find out the analysis for the common source amplifier with source resistance in series. Any doubt is there? So this is about a completion now. So now tomorrow class I will be just dealing with the source follower case. So now as of now common source with source resistance, any doubt is there, you can ask. Another doubt is there. At any point of doubt is there, you can ask right now only.
ಇಲ್ಲ ಸರ್.
So ಇದನ್ನು ಮಾಡಿಬಿಟ್ಟು, ಸೊ ಐ ವಿಲ್ ಆಫ್ಟರ್ ಫಿನಿಶಿಂಗ್ ಟುಮಾರೋ ಕ್ಲಾಸ್ ಆದಮೇಲೂ ಸೋರ್ಸ್ ಫಾಲೋವರ್ ಅಂತ ಇದೆ ಅಲ್ವಾ, ಆ ಸೋರ್ಸ್ ಫಾಲೋವರನ್ನು ಮಾಡಿಬಿಟ್ಟು ಐ ವಿಲ್ ಲಿಸ್ಟ್ ವಾಟ್ ಆ್ಯಂಡ್ ಆಲ್ ದ ಟ್ಯಾಬ್ಯುಲರ್ ಕಾಲಮ್ ಮಾಡಿಬಿಟ್ಟು ವಾಟ್ ಈಸ್ ದ ಇನ್ಪುಟ್ ವೋಲ್ಟೇಜ್. ಸೊ ಇನ್ ಕಾಮನ್ ಸೋರ್ಸ್ ವಿತ್ ಸೋರ್ಸ್ ವಾಟ್ ಈಸ್ ದ ಇನ್ಪುಟ್ ವೋಲ್ಟೇಜ್ ಆ್ಯಂಡ್ ವಾಟ್ ಈಸ್ ದ ಸರ್ಕ್ಯೂಟ್ ಡಯಾಗ್ರಾಮ್ ಎಲ್ಲದನ್ನು ಬರೆದ್ಬಿಟ್ಟು ಒಂದು ಶೀಟ್ ಆಫ್ ಪೇಪರಲ್ಲಿ ಬರೆದ್ಬಿಟ್ಟು ನಾನು ನಿಮಗೆ ಪೋಸ್ಟ್ ಮಾಡ್ತೀನಿ. ಸೊ ಅದನ್ನ ಪೋಸ್ಟ್ ಮಾಡೋಕ್ಕೂ ಮುಂಚೆ ಯು ಶುಡ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ಆ್ಯಂಡ್ ಅನಲೈಸ್ ವಾಟ್ ಈಸ್ ದ ಡಿಫ್ರೆನ್ಸಸ್ ಯು ವಿಲ್ ಬಿ ಎಕ್ಸಿಬಿಟಿಂಗ್, ಯು ವಿಲ್ ಬಿ ಗೆಟಿಂಗ್. ಓಕೆ, ಸೊ ದಟ್ ಈಸ್ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್. ಸೊ ಕಾಮನ್ ಸೋರ್ಸು ಮತ್ತು ಕಾಮನ್ ಸೋರ್ಸ್ ವಿತ್ ಸೋರ್ಸ್ ರೆಸಿಸ್ಟೆನ್ಸು, the gain is going to have a reduction, so by a factor of 1 plus gm into rs. So rs resistance ಆಗ್ತಿದ್ದಂಗೆ the gain value is going to reduce. That you should think. That is the important thing that you are going to have. But the bandwidth is going to increase, so the value of the resistance rs is going to act like a negative feedback action. So because of that, the gain value is going to reduce, as well as the bandwidth is going to increase by the same factor, 1 plus gm times of rs. It is going to increase. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? Okay, so I'll just conclude today's class. We'll meet you tomorrow.
Thank you, sir.
Okay, bye.
Thank you, sir. Bye, sir.
ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯನ್ರೋ ಹುಡುಗರ?
ಆಗ್ತದೆ ಸರ್.
10 marks in important question, 10 marks important question it is. Okay, so ಇದು ಡಿರೈವೇಷನ್ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಎಲ್ಲ ನಿಮಗೆ ನೆನಪಿರಬೇಕು. ಸೊ as soon as they give numerical also, they will be asking. ಸೊ ಇದನ್ನು ಕೊಟ್ಟರು ಅಂದರೆ ಅದ್ರ ಕರೆಸ್ಪಾಂಡಿಂಗ್ಲಿ ದೇ ವಿಲ್ ಬಿ ಆಸ್ಕಿಂಗ್ ಅಬೌಟ್ ದ ಪ್ರಾಬ್ಲಮ್ ಆಸ್ ವೆಲ್. ಸೊ ಇಟ್ ಈಸ್ ಅ ಜಾಕ್ಪಾಟ್ ಇದ್ದಂಗೆ, ಒಂದು ಕ್ಲೀನಾಗಿ ಕಲ್ತ್ಬಿಟ್ರೆ ಪ್ರಾಬ್ಲಮ್ ಸಾಲ್ವ್ ಮಾಡೋದು ಈಸಿ ಆಗುತ್ತೆ. ಸೊ ಐ ವಿಲ್ ಸಾಲ್ವ್ ದ ಪ್ರಾಬ್ಲಮ್ ಆಸ್ ವೆಲ್. ಸೊ ಬಟ್ ಫಸ್ಟ್ ಐ ವಿಲ್ ಫಿನಿಶ್ ಅಪ್ ದ ಥಿಯರಿ ಆ್ಯಂಡ್ ಐ ವಿಲ್ ಜಸ್ಟ್ ಟೆಲ್. Okay, bye. We'll meet you tomorrow.
Okay, sir.